So suppose it is equal to C. Yeah, we have only 3 of you. Okay, so I will wait for some more time, 2 more minutes, and then we will.
Excuse me, sir.
Yeah, yeah.
Actually, in the assignment you gave, sir, few questions are not taught to this fine elaborated. The osmosis related questions.
Yeah. Like that's why we didn't complete the chapter, but in your assignment we'll have all the questions covering the entire chapter. So once we complete it today, maybe we'll be able to solve every question.
Okay, sir.
Right? Okay. So that has questions covering all the parts of the chapter. There are a few things we didn't cover it yet, so we'll cover it today.
Okay, sir.
Yeah. So from these things we saw, from the portions which we see, and you tried to solve, is there any question you couldn't solve? Like, is there any topic anybody faced?
Question, sir.
Yeah, which question?
Just a second, sir.
Yeah.
I think it was question 12, sir. Question 12 or question 14.
What is the question? Is it a problem or?
It's a problem, sir. 12.
Okay. Question number 12. Let me check. Okay, so the question is that 45 grams of ethylene glycol is mixed with 600 grams of water. That one? Go on.
So I think it's what you're saying is the 10th question.
No, the 12th question is what I think 45 grams of ethylene glycol is mixed with that question, or?
I think so, that's so.
Okay. Fine. So they are, one second, let me click on the video. So yeah, so they're telling that I have 45 grams of ethylene glycol. Ethylene glycol is CH2OH, and CH2OH is dissolved in 100 grams of water. Right, that's what they're giving, and they're asking you what is the depression freezing point. They're asking what is delta TF. Okay, so it's direct formula substitution, right? Delta TF is equal to KF into M, where M is the molality. KF is given in the question. Delta TF is what you have to find out. Okay, so molality is what you have to calculate, and directly I think you can calculate what is molality, number of moles divided by the mass of solvent. Right, so number of moles of ethylene glycol you can calculate. So molality, how will you calculate? 45 divided by the molecular mass of ethylene glycol, and that would be 24, 26, 28, 30, 30 plus 32, right? 30 plus 32, 16, 32, 62. Okay, so 62 is the molecular mass of ethylene glycol. So 45 by 62 is the molecular, number of moles divided by the mass of solvent. Divided by the mass of solvent. Solvent here is water, 100 grams into 1000. That's it. You have to solve it. Very simple. Direct formula substitution.
Then I have another question, sir. 14th second one.
14th second part.
The second part of the question.
1 second. 14th. There is only one part. That is, so the question is solution containing 8 grams of substance and 100 grams of diethyl ether. That question?
Please, sir. No, sir. The question is,
1 second.
What happens when acetone is added to pure ethanol?
Oh, 1 second. What is the question you said?
What happens when acetone is added to pure ethanol?
Oh, when acetone is added to pure ethanol, it is going to form it is going to form an azeotrope. And I asked you to remember. Come back here. Yeah. So like whenever acetone is added to ethanol, right? So you have to understand that there is going to form an azeotrope. So whenever these kind of questions comes, right, something is added to this, what will happen? And all these questions, basically you have to answer in terms of azeotropes, right? So you have to tell that it is going to form maximum boiling azeotrope or minimum boiling azeotrope. And I asked you to remember what are the examples given in textbook. Okay, what are the examples given in textbook for maximum boiling and minimum boiling azeotropes that you have to remember, and accordingly you have to answer the question. Right? I think here in this case it is going to form minimum boiling azeotrope. If I'm not wrong. But please check it. Okay. So you have to tell that when these two are mixed, it is going to form an azeotrope, and what kind of azeotrope it is. That's it. That's all you have to answer. Nothing else.
Understood, sir.
Right? Okay. So I hope almost all of you would have joined. Yeah, I see so many people. Okay, fine. So then we'll right away start. Okay. Second. The duster is in very bad condition. I'll change the duster. Okay, fine. So last class, I think we were seeing about osmosis, osmotic pressure, diffusion, reverse osmosis. So all these are the terms which you should remember, right? Okay. So can someone tell me, okay, someone exactly define what is osmotic pressure?
Osmotic pressure is the amount of pressure to be applied to the side with lower concentration, so to stop osmosis.
Okay, so you have to tell it is the pressure which has to be supplied at the lower concentration side to just stop osmosis. The word just is very important. Okay, to just stop osmosis. Because when you are going to apply pressure greater than osmotic pressure, what will happen?
Reverse osmosis takes place.
Reverse osmosis, right? The solute particles are going to move from lower concentration side to the higher concentration side. Hope you remember the diagrams, everything, right? Hope you remember like it's like this, right? This is high concentration side, lower concentration side. This is where you apply pressure. Generally, the movement will be from higher concentration to lower concentration, right? But if you apply pressure greater than osmotic pressure, hope you remember what is the term which we use for osmotic pressure. Pi is what we use, right? So if the pressure you apply is greater than this, then reverse osmosis will happen. And I told you this is what is going to happen in your aquaguard, all the water purifiers you have in your homes, right? Okay, then we even saw an equation. Hope you remember the equation. What is the equation for osmotic pressure?
Is equal to CRT.
Correct. So you have pi is equal to C into R into T. And I told you how it's derived also. Like it's from ideal gas equation. So you don't worry about the derivation. It's all about the equation which you have to remember. This pi is equal to CRT, where pi is the osmotic pressure. What is C?
Molarity.
It's molarity. Please remember it is capital M, right? Capital M is molarity. And R value, what R value you have to use?
0.0821.
Yeah, you have to use 0.0821 and temperature should be in Kelvin. Please don't forget this. Okay, right. Fine. So now maybe we'll try to solve some problems on osmotic pressure. Right? Okay. So let me give you a question. Okay. Right on the question. Right. 200 centimeter cube. 200 centimeter cube of a solution of protein. The question is, I'm giving you the question, please take down. Right? 200 centimeter cube of an aqueous solution of a protein, okay, of a protein contains 1.26 grams of protein, right? 1.26 grams of protein, right? So the first statement is 200 centimeter cube of a solution, aqueous solution of protein contains this much amount of protein. Okay, right. The osmotic pressure of this solution, the osmotic pressure of this solution at 300 Kelvin, the osmotic pressure of this solution at 300 Kelvin is 2.57 into 10 to the power minus 3 bar. Okay, so the osmotic pressure of this solution at 300 Kelvin is 2.57 into 10 to the power minus 3 bar. Now the question is, calculate the molecular mass of the protein. Right? Calculate the molecular mass of the protein. Okay, then I'll repeat the question. 200 centimeter cube of an aqueous solution of protein contains 1.26 grams of protein. The osmotic pressure of the solution at 300 Kelvin is this much, 2.57 and 10 to the power minus 3 bar. Calculate the molecular mass of the protein. So I think this is what we have been doing for all the colligative properties, isn't it? We have to find the molecular mass of the solute. Unknown. I have a solute for which I don't know the molecular mass, but with the help of colligative property, we'll be able to find that out. And that's exactly what we're trying to do here also. Okay, right. So again, remember, osmotic pressure can be measured. Okay, it can be measured with a lot of instruments. You don't have to go into the details. Right, go for it. Now, guys, I just wanted to tell you one thing, right? So this pi is equal to CRTV, right? Okay. Now, please understand, depending on what is the unit of the pressure, right? Depending on what is the unit of pressure, the R value might change. Okay. Generally, I told you to 0.0821. Why? Because generally, if the pressure is in ATM, right? If the pressure is in ATM, then I can tell that it is going to, R value will be 0.0821. Right? Now, if you find, or even if you find ATM or mm of Hg, I can write like this: ATM or mm of Hg, or you can even have torr. Okay, so whenever you have all these units, then you have to use the R value as 0.0821. Right? But if you find that the pressure is given in terms of Pascal, bar, or Newton per meter squared, right? All these are SI units generally, right? So for this, you have to use R value as 8.34. Please remember this. Okay, right? But 99.9% of times you will see that this only will be coming. The pressure, the osmotic pressure will be measured in terms of ATM or mm of Hg or torr. For all these cases, you can use 0.0821, right? But whenever the pressure is given in terms of Pascal, bar, or Newton per meter squared, then you have to use the R value as 8.314. I think this comes from ideal gas equation. If you remember the ideal gas equation, in what cases what R value is used, right? It comes from that only. Okay, so in this question, please look at it. The pressure is given in terms of bar. Okay, remember, see, it's bar, right? So you have to use the R value as 8.314. Okay, yeah, now you can go for it. Okay, I hope it's just formula substitution. I think you should be able to do it.
61,000, sir.
Sorry?
So is the answer 61,000 gram per mole, sir?
61,000 gram per mole. Let me check once again. Where is the question? Yeah, so it's one question number 7. Yeah, 61,000 is correct. 61,039 gram per mole is correct. Okay. Fine. Let us solve this. It's just one equation which I have to substitute. Fine. So this is the equation. Phi is equal to C into R into T. Phi value is given 2.57 into 10 to the power minus 3. Concentration is molarity, right? So molarity is number of moles divided by volume. Number of moles of solute divided by volume of solution. Please be very careful, right? So a number of moles, they have given that the solute here is protein, right? So they tell that there is 1.26 grams of protein present in the solution, right? So the number of moles, if I calculate 1.26 is the given mass divided by the molecular mass, I don't know. Molecular mass of protein, I don't know, right? Okay. Now they have given the volume of solution to be 200 centimeter cube. Now please understand, people, 1 centimeter cube is 1 ml. Okay, 1 centimeter cube is 1 ml. Okay, this you have to remember. Okay, so 1 centimeter cube is 1 ml means 200 centimeter cube is 200 ml. So I can directly write the volume of solution is 200 ml, right? Now since it is in ml, I'll put 1,000, and R value we know is 8.314. Just now I mentioned, and the temperature is given to you. Temperature is what? 300 Kelvin. Okay, so everything else is known. Pi is this much. 1.26 pi m gives the number of moles of the protein divided by the volume. Volume is given as 200 centimeter cube, so 200 into 1,000 because it's an ml, and 8.314 is the value of R, and the temperature value is 300 Kelvin. That's it. If you calculate, you should be getting the molecular mass of protein approximately as 61,000 gram per mole. Right? Okay. I hope everybody understood, right? It's a simple formula substitution. We didn't do anything else big here. Okay, we'll go to the next question. So I am just looking for a good question. Okay, and maybe we don't have to. Fine. Cool. Like next thing, what you have to know, is this. I have something called as hypotonic solutions, hypertonic solution, and you have isotonic solutions. Okay, so we have three: hypotonic, hypertonic, and isotonic. Okay, so what do you mean by this, right? So please understand, here we are going to consider two solutions of same solute and same solvent. Okay, say sugar and water, another result sugar and water, right? Only when you have two solutions of same solute and same solvent, all these things can come into the picture. Okay, right. Now let us look into it. Right, so when I say, first we'll talk about isotonic. Okay, right. So what do you mean by isotonic solution? So if I have two solutions and if I call these two solutions together to be isotonic, right? So please understand, iso means same, right? And this tonic talks about the concentration, right? So isotonic solutions are going to have same concentration, right? Please remember this, right? So if I tell you that there are two solutions which are isotonic, right? So what do you mean by this is that I'm going to have same concentration for both these solutions, 0.5 m, 0.5 m, 0.5 m, like that. Okay, so now when I say hypertonic, okay, when I say hypertonic, right, then one of, so basically for these both hypertonic and hypotonic, obviously you can understand that it is going to, the concentrations are not going to be same, right? The concentrations are not going to be same. Now say let us talk about this. I have two solutions A and B, both same solute, same solvent, right? So assume that this is 0.5 m and this is 0.6 m. Okay, now please understand, hyper means higher, hypo means lesser. Okay, hyper means higher, hypertension means what? High amount of tension, right? Say hypo means lesser. Okay, so like we cannot, so you can understand that this is higher and this is lesser. Right, so what I can tell is, I can tell that B is hypertonic with respect to A, higher, right? B is hypertonic with respect to A. Same way, I can tell that A is having lesser concentration, isn't it? So I can tell that A is going to be hypotonic with respect to B. Hope you understand, right? Hyper is higher, hypo is lesser, right? So 0.6 is higher. So I will tell that B is hypertonic with respect to A. Same way, I can tell that A is going to be hypotonic with respect to B. Okay, so why are you even studying about this? Is because when you go for say injections, right? When you're gonna say take an injection for your body, right? So what will they do is, you're inside the inside your body, you will have some pressure, right? The blood flow will be there, other fluids will be flowing, so on and so forth, right? So whenever the injection is given, right? So please understand, for the injection liquid to go inside your skin, right? For the injection liquid to go inside your skin, you obviously in the syringe you see there'll be some pressing, right? So that pressure you supply, right? By pressing it, you apply some pressure, right? Okay, so only if there is high pressure when you supply, only then the liquid or the medicine can go inside your skin, right? So please remember this, right? So whenever the pressure is higher, then only it goes inside. Okay, now this is in terms of pressure. If I talk in terms of say concentration, please understand, inside the skin, the medicine, there is no medicine basically. Now only you're going to put the medicine, right? So inside the solution, there is no medicine, right? So that is why you tell that I'm going to take a hypertonic solution of the medicine. Again, I repeat, I'm going to take a hypertonic solution of the medicine. This will be higher concentration. What I have in the syringe will be higher concentration, and that goes inside the skin. Okay, so all these calculations should be there, right? Only when you're going to go for say syringe, all these things, right? There will be pressure variations, there will be concentration variations, and accordingly, what goes in which direction, all these things can be decided.
So could you
Okay,
repeat
now,
the last part about hypertonic and syringes?
yeah. So what I'm telling is inside your skin or inside your body, there is no medicine. So it is hypotonic, hypo. Right now, in the syringe, what you have is a concentration, and that concentration of the medicine obviously is higher than what is inside. Right. So this is hypertonic. This is hypotonic. So increase the pressure, and the medicine goes inside. Right. That's how it
Okay,
is.
sir. Understood.
Right. Okay. Now, one more thing is, right. When I talk about isotonic solutions, right. So when I tell you that there are two solutions that are isotonic, right. That means what? I told you that they're going to have same molarity or say same concentration. Okay. Now, if I take two solutions, A, B, both are having 0.5 and 0.5, right? At say 200 Kelvin. Okay, right? Both are having 0.5 and 0.5, and both of them are at 200 Kelvin, right? Can I tell that the osmotic pressure of both these solutions will be same? Can I tell that? Think about it, right? I'm telling both the concentrations are same and they are the same temperature. That means obviously their isotonic solutions are the same temperature. Can I tell that A solution and the B solution can have same osmotic pressure? Can I tell that? Yes, no?
Yes, sir.
Yes, sir. They'll have the same.
Yes, right? You can now easily see, I know pi is equal to C into R into T, right? Now forget about pi, we have to calculate for these two. Now C is same, 0.5, 0.5, R is obviously same because it's a constant, temperature is also same, right? So that is why we tell isotonic solutions in the sense they are going to have same concentration, and since they have same concentration, they will have same osmotic pressure. Please remember this. Okay, so when I tell that two solutions are isotonic, right, that means obviously that they're going to have same concentration, but that also means that they will have same osmotic pressure. So isotonic solutions will have same osmotic pressure. Is that what that's what you have to understand? Okay, maybe if we can solve a question based on this, just give me a moment. Just give me a moment. Just sorry guys, I'm not able to find the right book. But again, maybe I can give you some example. 1 second. Right. So all you have to understand is when I tell the two solutions are isotonic, they will have same osmotic pressure. That's what you understand. Okay. Right. Maybe I'll give you. I have to give you a question, but I think that like till now I have never seen questions coming like this in at least for CBSE boards. The questions might come for JEE mains and stuff. Fine, maybe we don't have to spend time on. We'll go to the next thing. Okay, so we have completed what is osmotic pressure, right? What is reverse osmosis, and what do you mean by isotonic, hypotonic, and hypertonic solutions? And we even solved a problem. See, problems are very simple when it comes to osmotic pressure. Actually, any colligative property for that matter, right? It's 99% of times it's going to be formula substitution, but again, you have to know how to calculate molarity, all these things you have to know. Okay, fine. So next thing what you're going to see is I already mentioned to you that we are going to use colligative property for finding the unknown molecular mass of a solute present in the solution. Right. Now, if I try sorry guys, I got a call. Anyways, right. So if I try to calculate the molecular mass, right. So for some of the solutions or some of the solutes, it's coming out to be correct. Okay, say for example, if glucose is a solute, glucose is dissolved in water, right? So I know the molecular mass of glucose is 180 grams, right? The molecular mass of glucose is 180 grams, that I know, right? So if I take any of the colligative property and I try to check it, I should be getting at least somewhere near 180 grams, right? And I do get it. In reality, we do see that it is almost close to 180 grams if at all if there is glucose in the solution. Okay, but if there is something like whenever you have something which can undergo dissociation or association, in the sense that, say for example, you have NaCl dissolved in water, right? Or say barium chloride dissolved in water, something, anything which can give ions, right? Or anything which can undergo association. What do you mean by association? For example, if you have BH3, right? Now I know 2 moles of BH3 can come together to form B2H6. This is dimerization, polymerization, we call it, right? So whenever I put BH3 in water, they will try to form B2H6. Okay, so whenever you have this kind of stuffs happening, right? Whenever you have this kind of stuffs happening, association or dissociation, I know NaCl will dissociate to form Na plus and Cl minus. BaCl2 will form Ba2 plus Cl minus. Now you see BH3 is getting dimerized to form B2H6, right? So whenever you see this kind of dissociation or association happening, right, the molecular mass value which you're going to get through the calculations, through the colligative property, will not be as expected. For example, I know the molecular mass of this thing is 58.5, correct, right? NaCl's molecular mass is 58.5. But if I do the colligative property and I calculate, right, so you will see that some of the times or most of the time it is going to be 117 grams. What do you see? That it is almost double, isn't it? 58.5 into 2 will basically giving 117. No, not exactly 117, say it will be around 1110 or 1112, something like that. But no way close to 58.5. That's all you have to understand. Right? It is not even close to 58.5, almost doubling. Right? Okay. So why is this happening? Why is there a mismatch? I know I should be expecting this much, right? But what I see in through calculations, this is the reality. I know in reality that it is 58.5. But if I try to calculate through the colligative property calculations, then I'm getting these kind of numbers, weird numbers, right? Now we have to understand why is such a kind of thing happening. But the same thing is not happening with glucose, right? Because glucose does not undergo any dissociation or association for that matter, right? So urea, glucose, any organic stuff, right? Anything organic will be okay. We'll be able to find it out. Proteins, right? We even solved the question for protein, right? So anything organic is okay for me. Like I'll be able to get the almost exact value, no mismatches, right? But whenever these kind of stuffs are happening, that is whenever you have an association or a dissociation, there might be a problem. You will not be getting what you expect. Okay, right. So we'll try to understand why this happens, but actually I forgot one important point about osmotic pressure. Okay, that we'll see, and then we'll try to answer this question. Okay, now we have 4 colligative properties, right? So 4 colligative properties are relative lowering of vapor pressure, depression in freezing point, elevation in boiling point, and the 4th and last one was osmotic pressure. Okay, right. So all of them are going to be used to find the unknown molecular mass of an unknown solute. Okay, now out of these 4, that is out of the 4 colligative properties, I am going to tell that using osmotic pressure is the best way, right? Out of the 4 colligative properties, right? Osmotic pressure is the best one to calculate the unknown molecular mass. There will be a question also, why? Right? Why is it that osmotic pressure is, say, way better when compared to all the other 3 colligative properties? Right? We have to basically like what do you mean by better? The accuracy of the molecular mass, right? That is going to be higher. I'll be able to predict accurately, more accurately, if I'm going to use osmotic pressure rather than using all the other three qualitative properties. Okay. Now the question should be why? Sir, why? Why is it like this? Right. Now, two things are going to be very, very important. Right. So why osmotic pressure is better than all the other three qualitative properties? First one is temperature. Right. Now, say when you go for elevation and boiling point, or say depression and freezing point, what you have to do for say elevation and boiling point, you have to heat the solution to the boiling point. You have to increase the temperature, isn't it? Right. Same way for depression and freezing point, you have to keep on decreasing the temperature. Then only at the freezing point or only at the boiling point, I'll be able to do some calculations. Right. But in case of osmotic pressure, you see that can even happen at the room temperature. That's the very, very good advantage. Right. Now, why is it an advantage? Why is it that temperature increase or temperature decrease is a problem? Is because whenever temperature increases, certain bonds can break. Some other reaction can happen. Same way when I go for decreasing the temperature, some other reaction might happen, right? So osmotic pressure is one very it's better because we can do the calculations or we can do the experiment at room temperature. Like instead of writing temperature, I can write it as room temperature itself. But for elevation and boiling point and depression and freezing point, you have to either increase the temperature or you have to decrease the temperature. Okay. Fine. So then what about what is that? What about that relative lowering of vapor pressure? Why are you not using it? That can happen at room temperature itself, right? Still, I'm telling that osmotic pressure is going to be what to say? Osmotic pressure is going to be favorable. Why? Because now you see delta P divided by PA naught. This is what is relative lowering of vapor pressure, isn't it? And you have pi. That is the osmotic pressure. Right. Now, please understand, people, the numbers of this, the values of this and this, if you compare, right? Now, this value, that is relative lowering of vapor pressure, is a very small value. Okay. And measuring it will be very difficult. Okay. That del P divided by PA naught, relative lowering of vapor pressure value is very, very small value. Right. But osmotic pressure, you would have seen in this thing, it will be a significant value. It will have some good number to work with. Okay. Say 0.000 something is really not going to help me. Like the accuracy will be very less. Calculation will be difficult. Right. Now, second reason that why osmotic pressure is higher, better, is because it is going to give me a significant value. Right? It is going to give me a significant value, or not only relative lowering of vapor pressure, even your depression and freezing point or the elevation boiling point. It will be what? Say it will be 100 degrees Celsius to 101 degrees Celsius. Value will be 1. Right? So nothing much to work with. Okay, 1 is actually a very big deal. Sometimes you will see lesser than 1 also. Okay, so the value of osmotic pressure which you can measure will be a significant value, higher value, and you can easily calculate the other stuffs, right? But all the other three are going to be very, very small values, right? So calculation will be difficult, accuracy will be less, right? So that is why we say that osmotic pressure is the best colligative property for which to calculate the molecular masses. Two reasons. One is it can happen at room temperature itself. Second reason is that it can have a significant higher value compared to all the other properties. This is a very good. This question has been repeating so long time. So please remember this. Why osmotic pressure is better? Okay, so I hope everybody understood why osmotic pressure is better. Right. Now we'll go back to the problem we are facing. Right. So if I have glucose or any other organic substances, the molecular mass calculation, whatever I'm getting through the colligative property is okay. It's almost matching. Right. But I told you, whenever you have this association or dissociation, right, there is always a problem. Now you see, I told you the molecular mass of this thing is expected to be 58.5 from the calculation, but see what values you're getting. You'll be getting 117, 1110, 1112. Same goes for BH3 will be half. Say you can calculate. For boron, it is molecular mass, atomic mass of boron is 10, right? 10 plus 3 will be 13. This is what we expect, right? But what will you see in reality? What will you see? Not reality. This is what we expect in reality, right? But what will you see through the calculation is that you will be getting around 6 grams or 7 grams, right? 6 grams or 7 grams is what will you see from the calculations. Okay, now why is it happening? And first thing is why is it happening? Second thing is how can we correct it? Right, from the colligative properties, we have to calculate correctly what we have to do. Right, so before that we have to understand why is this happening. Okay, fine. Now this is happening is because of how colligative properties are defined. Right, so we know what is the definition of colligative properties. Right, colligative properties are the properties which does not care what is there, it just cares about how much is there. Right, okay, so it doesn't care, it doesn't know what is there, but it is just dependent on the amount of substance rather than the type of substance. That is how we define the colligative property, isn't it? Okay, fine. Now say if I take NaCl, NaCl is the solid form is okay, but once I dissolve NaCl in water, NaCl is a single entity, right? NaCl is a single entity. Sodium chloride is a single entity, right? Now, this single entity will form Na plus and Cl minus, in the sense it is going to form two different entities, Na plus and Cl minus. Right, now we know it is same, right? Na plus and Cl minus only will come together to form NaCl. We know that, right? But colligative property doesn't know that, right? So what colligative property will think is NaCl is one component, but by the moment I dissolve it in water, it is becoming two component system, right? Na plus and Cl minus, both are there, right? So like assume it like this. For example, I'm going to take osmotic pressure. Okay, so if I tell that I'm going to have 0.5 m HCl, sorry, 0.5 m NaCl, right? Now when you go into the solution, what will happen? I will have 0.5 m of Na plus and 0.5 m of Cl minus. Now, what is total concentration now? Total concentration now will become 1 m. It's not happening, please. It's not happening in reality. But this is how colligative property will think. Because colligative property doesn't know it's an ionic compound, doesn't know it's a covalent compound. We know that ionic compounds will ionize to form cations and anions. It is eventually same as the compound itself, right? But what you see is initially it was 0.5 m. This is how the colligative property sees it. 0.5 m. Now the amount has increased. That is what colligative property sees, right? The amount has increased. It doesn't know what is there. It doesn't care what is there. It all cares about is how much is there. Now you see now how much is there is a problem now. It became 1 m. 0.5 m is what we know. 0.5 m only should be there for NaCl also, but it is going to treat this separately, that separately, and obviously, if you're going to do the calculation, assuming that this is like this, and obviously that is why you're getting a double the value. We expect 58.5, but you see pi is equal to C into R into T, right? The value will be double because it is going to become 1. Okay, right? So hope you get the point. Why is it that I'm going to have a mismatch? Right, same thing here. Say if I consider that it is going to be 1 m, right? Now when this undergoes association, the colligative property will assume that it is going to be only 0.5 m. Again, because it doesn't understand that it is the same compound undergoing dimerization. Right, we know that because we know what are organic, what are ionic compounds, what are covalent compounds, what is association, what is association. We know that, but colligative properties will not know that because that is how they are defined. Right? Okay, that is why we are seeing a mismatch. Everybody understood why is there a mismatch? Can everybody give me a yes in the chat box or in the unmute yourself and speak? Is it okay?
Sir, can you explain the BH3 part, sir?
Yeah, sure. So you see, BH3, assume that I have a BH3 solution of 1 m concentration. Okay, now we know it's going to be two more, like basically if you take one of this, right? Now two molecules of this will become B2H6. Okay, so what will happen now? 1 m will get converted to 0.5 m. Again, it's not getting converted. It is not getting converted. But this is how colligative property will assume it to be. Right? So it all depends on the number of, say I had 1000 BH3s initially, right? Now what will happen in solution? 1000 BH3s will form only 500 B2H6, right? What do you see? The amount is different, right? This is the actual amount. This is the amount after the association. We understand this, but your colligative property will understand this. What value we should have taken is this value and calculate, right? But what value the colligative property will take and calculate is this value. That is why you see the molecular mass is half of what I expect, right? But here you see, here you have 0.5 m. This is the value we should have taken and calculated. But colligative property will assume that this is what is happening, 0.5 and 0.5 for Na plus Cl minus. So the concentration taken in the calculation will be different, and obviously the molecular mass will be different. Yes, understood?
Yes, sir. Thank you.
So I have a doubt.
Yeah, please tell.
So in exam they ask the reason for difference. What exactly should we write, sir?
You should tell that it is because of association or dissociation. So after association or dissociation, the amount or the number of particles will change, right? And the colligative properties will depend on the amount. And obviously there is a mismatch. Yes?
Okay, sir. Understood.
Okay, right. Okay. So done. So we understood why is it happening. Right. The next thing what we'll try to see is how are we going to correct it. Right. Fine. Okay, so for correcting this mismatch, what we'll try to do, we'll see. Okay, so for correcting this, people, I have a factor. There is going to be there was a scientist who observed this, and he was the one who gave a suggestion that you can do this so that you will be able to get the correct value. Okay, so we are going to introduce a factor. We are going to introduce a number which is going to help us. Okay, that number is what is called as your Van 't Hoff factor, and is written by the letter small I. Okay, we are going to use this factor in our calculations to avoid all the mismatches we are talking about. Okay, so Van 't Hoff factor is given by the scientist Van 't Hoff. Is a scientist. Okay, so I is what we determined. Okay, right. Now, how am I going to define this? You see, right? I is equal to experimental colligative property by calculated colligative. Okay, experimental colligative property divided by the calculated colligative property. Please look at this. Say I will take any of that. Say any of the colligative property. I take, say I take diffusion freezing point. Something I take delta TF is KF into M. Okay. Now, what do you mean by experimental? What do you mean by calculated? Now, please understand, people. This is the formula. KF into M is the formula to calculate delta TF. Right. Now, this KF into M is what is my calculated. Right. But this delta TF can be measured also. Like I can take a thermometer and measure it. Right. Now that is experimental. So this is experimental that I can measure, or you can even write measured colligative property, or actually it's better, right? You can write it as measured colligative property divided by the calculated colligative. Right. Obviously, this delta TF is measured KF into M. Obviously, if you know the KF and if you know the modality, you will be able to calculate what is the delta TF. That is theoretical, calculated. Right? You can tell calculated or it is theoretical. Right? And that is measured, or I can write it as experimental colligative property that I'll be able to measure. Right? So this is experimental. KF into M will be calculated. Same goes for all the other colligative properties. Say pi is equal to C into R into T. C into R into T is the calculation. Right? This pi is the measured one. Right? And this is calculated. Okay, so what it tells you, obviously, right, there will be a mismatch because that I will have some concentration problem here. Also, I'll have some concentration problem, right? That is why the calculated and the measured value will not match because of reason I told you earlier. We saw in the previous section. Well, how is there a problem? Okay, so the measured value and the calculated value will not be same for certain things. For glucose, urea, and all the organic stuff, both these values will be almost same, right? But this case, all the other cases where association or dissociation can happen, right? In all those cases, the measured colligative property and the calculated colligative property will be different, right? So obviously, to make this equal, I can include a term, right? That term is what is meant. Okay, which is defined as measured colligative property divided by the calculated colligative. Right. So if I can little bit expand this, right, I can write it like this: measured is equal to I into calculated. From this, just put this here, and you can name it the measured is equal to I into calculated. Van of factor into the calculated value. So now, if you include this Van of factor in all the equations of colligative property, you have 4 colligative properties. In all the 4 colligative properties, if you include this Van of factor I, then all the problems you face because of association or dissociation can be avoided. Right? So how do we do it? See that it's very simple, right? So for anything, say if I take relative lowering of vapor pressure, delta P divided by PA naught, we just write XB, right? But you include the one. This is calculated. XB is calculated. This can be measured, right? So you put an I. So delta P divided by PA naught is equal to I into XB. Same way, delta TB is equal to KB into M, calculated, measured. You put an I here. Right, same way, delta TF is equal to I into KF into M. Again, KF into M is calculated, delta TF is measured. You see, measured is equal to I into calculated, I into calculated. Everywhere is I into calculated. Same way, for pi is equal to I into C into R into T. Again, CRT is calculated, pi is measured. You include a I in the calculated side. Right? So all these modified equations with the help of Van of factor are going to give us the correct colligative property, and by that way it is going to give me the correct molecular mass also. Is it fine? Okay, right. Now, yeah. So one way of defining the Van of factor with the help of the colligative property, the other way of defining the Van of factor is through the molecular mass. Obviously, there will be two changes in two things, right? One is in the value of the colligative property. There will be a mismatch between the measured colligative property and the calculated colligative property. Obviously, the other mismatch will be in terms of molecular mass. Correct, because we know we expect a molecular mass, and the molecular mass obtained from the calculation is it's not coming out correctly, right? So by that way also I'll be able to define what is the Van of factor. So that we'll see. It's very simple, right? So what we are going to do is, now please understand, for any of the colligative property, say for any of the colligative property, and you see how is it related to the molecular mass. Okay, how is it related to the molecular mass? You can easily understand. Say pi will be there. If you take C, what is C? It is number of moles by volume. Again, what is number of moles? Given mass by molecular mass. Correct. Now, what do you understand? Any colligative property is inversely proportional to the molecular mass. Okay, any colligative property is inversely proportional to the molecular mass. Okay, right. So, anyways, now you don't have to remember this, but still, it's a very good thing to remember. So, I, in terms of molecular mass, how do we write? Is calculated molecular mass divided by expected molecular mass. I can write it like this. Okay, calculated molecular mass divided by expected molecular mass. Okay, calculated means what? Calculated through the colligative property calculation. Expected is what we already know. Say for NaCl, it is 58.5. That I know. That is what is expected. Right? Calculated colligative property is going to come from the calculations. That is from the colligative property calculations. Okay, right. So, right. Say if I have NaCl becoming Na plus plus Cl minus, right, and assuming that it is going to have 100% dissociation, right? Assuming that I'm going to have 100% dissociation. Okay, now remember, whenever you have 100% dissociation, not only for this, for any of the compounds, right? So here you see one thing becoming two things. Okay, so what I understand is the molecular mass will also be doubled. Okay, if one thing becomes two things, the molecular mass is doubled. So I can easily tell, say if the calculated was 117 grams and the expected one was, I know it's 58.5, and you know the Van factor will be 2. Okay, this is the calculated molecular mass. Whatever the colligative property you want to take, and you calculate this, right? And if you calculate, assuming that it is 100% dissociation, right, you will get the value of the calculation to be 117 grams, right? But what we expect in reality would be 58.5. Okay, right? So this divided by this, the Van't factor will be 2. So I think you will be able to observe certain things here, right? So what I'm trying to tell you is, if 100% dissociation, right, the I value will be equal to number of particles after dissociation or association. Is it not? Right? If I have 100% dissociation, what I see from this, whatever the calculation which I did now, is that if there is 100% dissociation or association for the matter, we don't know, right? Like, it depends on the compound, right? So, but if there is 100% dissociation or 100% association, the Van't factor I will be equal to the number of molecules associated or dissociated. In the sense, you see, one molecule is becoming two molecules. In the product set, what you see is what is important. Okay, so here you see the number of molecule, one is becoming two, so the Van't factor will be 2. You can see here, I calculated the Van't factor is 2. Right? Say if this was BH3 becoming B2H6, right? So here I have 2, here I have 1. Or if I write 1 here, this will become 0.5. Right? So here the number of molecules after association is 0.5. Again, 100% association, right? So for this case, the I value will be 0.5. Okay, for this case, I value will be 0.5, and whenever dissociation happens, after dissociation, how many molecules you have, how many components you have, that will be the I value. Say, for example, if I take AlCl3, can you tell me what will be the Van't factor, assuming 100% dissociation? Yeah, right? If I have AlCl3, assuming 100% dissociation, what will be the Van't factor? And come on, it's just a guess. What will be your guess?
So can you repeat the question?
Assuming that AlCl3 undergoes 100% dissociation, what will be the Van't factor for AlCl3? Now, looking at all this, I told you here it is 2, here it is 0.5, there it will be how much? What did I tell you? I is equal to number of particles after dissociation. Right? So after dissociation, what will happen? What are the ions formed here? Please tell me.
Al3 plus.
Al3 plus and
3Cl minus.
Okay, Al3 plus and 3Cl minus.
Sir, is it 4, sir?
Yes, 4. Obviously, right? You see, one molecule is becoming 1 Al3 plus and 3Cl minus, totally 4. So the Van't factor will be 4. Again, assuming 100% dissociation. Okay, I think everybody understood. Say if it was MgCl2, what would have been the Van't factor? 100% dissociation.
3, sir.
3. Right? MgCl2 will give Mg2 plus Cl minus. Okay, right? So totally 1 Mg2 plus 2 Cl minus will become 3. Again, remember, this will happen on and only if 100% dissociation is there. Okay, so then what if I have say 70% dissociation or say 50% dissociation only is happening, right? Then the Van't factor will not be exactly 3 or exactly 4 or 0.5 exactly. No, it cannot be like that, right? So how are we going to calculate? Right. Okay. Now I already gave you two definitions for Van't factor. One in terms of colligative property, the other in terms of molecular mass. Now I'm going to give you another definition. Okay. Another definition is I is equal to total number of moles at equilibrium. Okay. Don't worry about it, right? It's very easy. right? So I is equal to total number of moles at equilibrium. Okay, right. Now, please understand, people, we are talking about how much dissociation is happening, right? How much dissociation is happening, right? So please go back to your 11th class and go to the equilibrium chapter. Which quantity will talk about the amount of dissociation? Can you think of a factor? Can you think of a number or some quantity which will talk about the amount of dissociation? What is that? What is the value? What is the name of the value?
Equilibrium chapter, sir.
Yeah, in equilibrium chapter, say we tell, right, if I have HA becoming H plus plus A minus, this is dissociation of an acid, right? How much dissociation is happening is given by a factor. What is the factor, or what is the value? Name of the value?
Enthalpy dissociation, sir.
No. So it directly gives me what is the percentage association, but again, not in terms of percentage, but in terms of something else. So do you guys remember this alpha? Yes, do you guys remember this alpha? Can you tell me what is alpha in equilibrium?
Degree of dissociation.
Yeah, it's called degree of dissociation. Okay, alpha is called degree of dissociation. Okay, from the name itself we can tell how much dissociation is going to happen. Okay, but in this case, well, since I'm using for both association as well as dissociation, it can be degree of dissociation or degree of association, doesn't matter. Okay, so if I find that the alpha value is 0.1, now remember, alpha value will be between 1 and 0, right? When I have a value of 0 means what? No dissociation, no association. When I have the value of 1 means what? 100% dissociation. So remember, alpha into 100 will give me percentage dissociation. Okay, well, alpha into 100. So 1 into 100 is 100. Means what? 100. Excuse me. Right. So 1 into 100 will become 100% dissociated. Okay. So alpha value will be between 0 to 0 and 1. Right. So depending on what is the value of alpha, that value into 100 will give me the percentage dissociation. Okay. Right. So this is what we are going to use, because I told you I value, the Van 't Hoff factor, is going to depend on how much dissociation is happening. Right. If it is 100% dissociated, it's very easy. Right? But if it is not 100% associated, then we have to take the value of alpha and then check it. Okay, so for that, the definition I gave you is going to help here. I is equal to total number of moles at equilibrium. When I say total number of moles, it is about the reactant as well as the product. Right? Obviously, if it is not 100% associated, if the reaction is not 100% completed, obviously there will be some amount of reactants also. Right? If there is 100% completion, whatever be the amount of reactant, entirely it is going to go to the product. Right? But we know 100% dissociation or 100% completion of reaction is very rare. Right? So eventually you will always see some amount of reactants also present, because it is not going to be 100% completed. Okay, so all those things, how much is happening, how much is happening, all those things will be given by this term alpha. Okay. Sorry guys, again I got a call. Okay, so we'll try to understand what do you mean by this and how am I going to connect my I and alpha. We'll try to see. Okay, right. Say I take NaCl. Right, NaCl will form Na plus and Cl. Okay, now assume that I take only 1 mole. Not only for this case, for any of the case, you assume that initially I had 1 mole of the particular compound. Okay, this is initial. Okay, now initially assume that there are no Na plus Cl. Okay, right. Now at equilibrium, obviously the reaction will complete, right? And eventually the reaction is going to stop. Right. Now, if the reaction was going to stop means it doesn't mean that it's 100% complete. Right. Equilibrium can be attained. It doesn't mean that I can have 100% completion. The reaction has stopped. Doesn't matter whether it's complete, whether it's 100% complete or not. Okay. Right. Say among this 1 mole, some amount of NaCl would have gone to become Na plus and Cl minus. Okay, and that amount out of 1 mole, how much has gone to dissociate? That amount is what is my degree of dissociation. Is it not? Right? Say if I write 1 minus alpha, alpha is the degree of dissociation. Right? Out of 1 mole, how much has gone to dissociate is what is my alpha. Right? Remember the scale is between 0 to 1. Right? So out of 1 mole, how much is going for dissociation or how much is going for association? That is what is alpha. Right? So out of 1 mole, some alpha moles would have reacted to form Na plus and Cl minus. So what will be the value? What will be the number of moles of Na plus and Cl minus? Can you tell me here and here what value should come?
Alpha, sir.
Yes, alpha and alpha. For both of them, it is alpha and alpha because 1 mole of this gives 1 mole of Na plus and 1 mole of Cl minus. So if alpha moles are reacting, alpha moles of Na plus and alpha moles of Cl minus. Okay, now going to this, I is equal to total number of moles at equilibrium. So if I want to calculate I have to sum up all the number of moles. Na plus is the number of moles, Cl minus is the number of moles, also the number of moles of X. Total number of moles at equilibrium. Right? So 1 minus alpha plus alpha plus alpha. Right? So one of the alphas gets cancelled. So you will get 1 plus alpha. Right? So I value in this case is equal to 1 plus alpha. Again, depending on the alpha value, the I value will change. Now, please see, if I have 100% dissociation, if I have 100% dissociation, what is the value of alpha? If I have 100% dissociation, what is the value of alpha?
1.
1, right? 1 means 100%. So you see, if I put the value of 1, what will happen? I value will become 2, and that's exactly what we saw previously. NaCl becoming Na plus plus Cl minus, right? Or I told you, if it is 100% dissociated, the I value will be equal to what has formed, how many number of components it has formed after the dissociation. After dissociation, it is 2, so I value becomes 2. So now in this case also, you can check, I proved to you that the I value is equal to 1 plus alpha. And I told you if alpha is 100, if I have 100% dissociation, alpha value is 1. Now if you substitute the value for 100% dissociation, you are going to get the I value. But again, this will not happen every time, right? So don't worry about it. So if I have NaCl, this kind of compound, I told you that I is equal to total number of moles at equilibrium. You can easily calculate it.
So I have a doubt here.
Yeah.
So we always take 1 mole, right? Nothing
We always
except
take
1
1.
mole.
Yeah, we always take 1 mole. Yes. Okay, we'll see some more
So one
examples.
more
Yeah,
doubt.
yeah.
So when do we use this to find what for I? How do we know where to use which I formula?
I understood. I understand. We'll solve some questions. So basically, if in the question, right? If in the question they will not directly tell you that you have to use quantafactor stuff, right? But in the question, if they give some amount of NaCl or some amount of AlCl3, some amount of MgCl2 is dissolved in water. By the moment you see any ionic compound, any solute which is ionic, you have to use quantafactor. Okay, but if they give a question like 100 grams of glucose or say 50 grams of urea is dissolved in an amount of water, then you don't have to worry about any of this because I know that there will not be any of this, there will not be any dissociation. But the moment you see any ionic compound form, ionic compound present in the solute, you have to go for that. Okay,
sir.
and if they are not going to give you any amount, anything saying that this is the amount of dissociation, 50% dissociated or 70% dissociated, if they are not going to give you that, assume it to be 100%. Okay, if you assume it to be 100%, you know what will be the Van factor. So you directly substitute in the form. Are you able to understand what I'm saying? Right?
Yes.
Okay. Good. We'll solve questions. Don't worry. We'll solve a lot of questions on that. Okay, right. So maybe we'll take one more. Yeah, question. Yes.
Even if they give 70% dissociation, Can we take alpha as 0.7, sir?
Absolutely, we cannot. We can we take 11? We have to take the alpha value as 0.7.
Okay, sir.
Okay, right? So if depending on what is the value, what they give you in the question, the amount, degree of percentage dissociation, accordingly you will take that.
Okay, sir.
Okay, right, good, fine. And maybe we'll take one more example like this. Say, let me take say MgCl2, right? I know NgCl2 will form Mg2 plus and 2Cl minus. Okay, say initially I take 1 mole, 0, 0, right? At equilibrium, right? Say now some alpha would have reacted. What should come here? Mg2 plus. Sorry?
It will be alpha, sir.
Okay, for Cl minus? No, it's just
2
it
alpha,
is
sir.
2 alpha. Please look at this. I have 1 mole of MgCl2 giving 1 mole of Mg plus, so it's okay. Alpha moles will give alpha moles, right? But you look at here, 1 mole of MgCl2 gives 2 moles of Cl minus. So if at all alpha moles are reacting, you will form 2 alpha moles of Cl. Okay, be very careful among this. Okay, right. So now what I do, I can calculate what is the I value. Again, I value is defined as what? Total number of moles at equilibrium. So you sum up all of these. So 1 minus alpha plus 2 alpha, right? So this alpha gets cancelled. So I value in this case will be equal to 1 plus 2 alpha. Okay, right? Again, depending on the alpha value. Now, if I put alpha value as 100, I mean 100% of the alpha value as 1. So what will happen? 1 plus 2 will become 3. Again, you can see there are 3 ions after dissociation. 1 Mg2 plus and 2 Cl. It's totally becoming 3. Right, one more example we can see. This time maybe you do it. Okay, say I have sodium sulfate. Right, go for it and tell me the connection between I and alpha.
Equal to 1 plus 2 alpha, sir.
Yeah, right. So now it will form what? Na2SO4 will form 2Na plus SO4 2 minus. This is what is dissociation, right? 2Na plus SO4 2 minus. Again, initially 1 0 0 at equilibrium 1 minus alpha. Now here, what should come?
2 alpha, sir.
2 alpha. Again, 1 mole of Na2SO4 gives 2 moles of Na plus, right? So again, 1 mole of this will give only 1 mole. So here it is 1. So I value, I sum up all this 1 minus alpha plus 2 alpha plus alpha. Again, you'll get 1 plus 2 alpha. Okay, very easy, very easy, right? Maybe we'll get around for the association. Say BH3. We'll take what happens. Okay, say I take BH3, I'll take 2 moles of BH3 becoming B2H6. Okay, right? Say initially 1 and 0. Okay, now at equilibrium, now please remember people, right? If, okay, fine. If I write 1 minus alpha, what should come here?
It should be alpha.
Alpha? Look at it properly and tell me. Look at this. Look at the numbers here and here and tell me what should come here.
Alpha by 2, sir.
Absolutely. Right. You see, 2 moles of BH3 gives 1 mole of B2H6. Right. So if alpha moles are reacting, I will be getting alpha by 2 moles of B2H6. Please remember this. Okay. So 2 moles gives 1 mole. So alpha moles will give me alpha by 2 moles. Okay. So here it should be alpha by 2. Okay. Now again the I value is same. Total number of moles at equilibrium. 1 minus alpha plus alpha by 2. Can I say it will be 1 minus alpha by 2? Right, that is the I value. Okay, so like this, like see in your book they would have given you a formula connecting I and alpha, right? That I really will not suggest you to remember the formula because it's little, I don't prefer it, right? So you can remember this very easy, right? You go for dissociation, you write the alphas and calculate the total number of moles at equilibrium and connect with the I. Okay, everybody understood. Now any electrolyte is something which will give ions. Okay, so any ionic compound is given to you, right? Will you be able to get the connection between I and alpha? Everybody will be able to do it. Please give me a yes, or if at all anybody still finds problem, please let me know. Is everything okay till now?
Yes, sir.
Okay, others,
Yes.
please tell me. Okay, fine. I
What
suppose
was the I
everything.
value for this, sir? The 2BH3
In this
should be
case,
2H6.
I value will be 1 minus alpha plus alpha by 2. So it will become 1 minus alpha by 2. That is the I value.
Okay.
Right? Same thing. It's the definition is same. Okay. Fine. So maybe we'll just do one problem, and that's it. This is guys. That's it. That's it. The chapter is over. Right? We just have to do some problems. Maybe next today's class we almost have 10 more minutes, so we'll do a problem. Right? Next class we'll do some 3-4 problems, and then we'll go for the next chapter. And next chapter will be electrochemistry. Okay. So what is going on in your other chemistry faculty? I think he's taking haloalkanes, haloarenes. Is it completed?
Yes, sir. He finished, sir.
He finished it. So I think he would have started alcoholic phenols.
No, sir.
No,
After
sir.
Then what did he start?
yesterday he finished, I think, haloalkenes, haloarenes. After yesterday he finished.
Oh, yesterday only he completed. Okay, fine. Okay. Right. So let us do some problems. That's what we are waiting for. Okay. Uh, just a moment, people. There are questions, but I just want the right question to come to you. Okay, fine. Take down. The freezing point of a solution. The freezing point of a solution freezing point of a solution which is obtained by the freezing point of a solution which is obtained by dissolving the freezing point of a solution obtained by dissolving 5.85 grams of NaCl. 5.85 grams of NaCl in 100 grams of water. In 100 grams of water is minus 3.348 degrees Celsius. Right? 5.85 grams of NaCl in 100 grams of water is 3.348 degrees Celsius. Okay. Now the question is, calculate the Van 't Hoff factor for this solution. Calculate the Van 't Hoff factor for this solution. Right? So they are given Kf for water to be 1.86 Kelvin kg per mole. Okay, I'll repeat the question. The freezing point of a solution which is obtained by dissolving 5.85 grams of NaCl in 100 grams of water is minus 3.348 degrees Celsius. Calculate the Van 't Hoff factor for the solution. Okay, right? Now see, they are given NaCl. Like, even if they did not, like, if the question was not about Van 't Hoff factor, something else, the moment you see NaCl, you have to understand that you have to use Van 't Hoff factor, because I know it'll undergo dissociation. Okay, right. Please go for it. Right. So they have. It's very simple, people. Now it has nothing to do with degree of dissociation. Nothing. They're directly asking you what is the Van 't Hoff factor. You know how to calculate, right? So I gave you the modified equations of the colligative properties, right? So you know there is an I somewhere there. Use it and find out. So if at all you remember, it's a depression and freezing point. Delta TF will be equal to I into KF into M. This is what is the equation you have to use. The moment you see any electrolyte, anything which is ionic, or anything which undergo association, you have to understand that you have to put the I. This is the measured value. This is the calculated value, right? Now see that minus 3.03 mean minus 3.348 is the freezing point. But what you have to do, you have to calculate depression in freezing point. And what will be that value? Can you tell me? What will be delta TF for this question? What will be delta TF for this question?
KF into M, sir.
No. I'm asking about the value. Leave about this. What is the value of delta TF in this question?
Less 3.348, sir.
Yes, absolutely. Right. You know, freezing point of water is 0 degrees Celsius. See, they will not give it like this. Okay. The freezing point of water is 0 degrees Celsius, but after adding NaCl, it is becoming minus 3.348. Right. So you have to take the difference. 0 minus of minus this. So the value of delta TF is 3.348. Okay. And I is what we have to calculate. Kf is given, which is 1.86. M you have to calculate again. Molality you have to calculate. You know how to calculate number of moles divided by mass of solvent. Right. So they have given the given mass to be 58.5.85. This is the given mass divided by the molecular mass, that is 58.5. right? Maybe I'll write it at the top. So I'll write like this. 3.348 is equal to I into 1.86. That is Kf into M. Molarity value you have to calculate. Molality will be a number of moles. That is 5.85 divided by 58.5. This is the number of moles divided by the mass of solvent. The mass of solvent is what? 100 grams of water into 1000. That's it. So this is what is the fact. Okay, so this is one type of problem which can be asked. The other type of problem can be including the alpha value, telling it this dissociation happening, all that. We'll maybe solve it in the next class. Okay, right? So I hope everybody understood how to do this problem.
So what's the final answer, sir?
Final answer, let me check. This is what? This is short answer type 1. Question. So 1.8 I value, you will be getting it as 1.8.
Yes, sir. Got it.
Okay, now tell me what is the percentage dissociation? For the same question, I ask you two things. One is the Van 't Hoff factor. Second one, I want to know what is the percentage dissociation. Can you tell me the answer? Calculate and tell me. I told you how alpha and I are related, right? I want to know what is the percentage dissociation. Tell me the answer.
So 80, sir. 80,
I don't know, maybe. Okay, I think it should be correct, I guess. Right? You know how to connect my alpha and I, right? So it is NaCl. So NaCl will form Na plus Cl minus 1, 0, 0, 1 minus alpha, alpha, alpha. So can I write I value as 1 plus alpha?
Yes, sir.
Right. Now I value is 1.8, 1 plus alpha. So can I write alpha as 0.8? Right? 1.8 is equal to 1 plus alpha. So alpha value will be 0.8. So obviously percentage dissociation will be 100 into this. So I have 80% dissociation. Okay, the same question can be asked in this way also. Or they can give it like this, right? They can tell that 80% dissociation is happening, and they can ask you what is the alpha I value, something like that. Lot of modifications can be done, right? We'll solve it. Like we'll solve good questions next class, right? I hope everybody understood what we're trying to do here. Okay, first
Yes,
is easily calculating the I value, and from the I value, you know how to connect my I and alpha. You can calculate the percentage dissociation also. Okay, fine. So I will take another maybe half an hour next class, and then we'll start. So we'll start with electrochemistry. Okay, right. If there are no questions, yeah, please.
Just say the formula for osmotic pressure with Van 't Hoff factor, sir.
Nothing. It's very simple. We know pi is equal to C into R into T. You just include I after the equal to I into C into R into T. That's
Okay, sir.
right. Okay. Any other question, people? Anything else you want to know?
So when we use that I equal to calculated molar mass by experimental molar mass.
Sorry.
That calculated molar mass by expected molar mass. When do we use that, sir?
Oh, that will be questions like this. Like say the question will be like they will give it. Say there is a compound whose molecular mass is this much, right? And they'll tell in the question that through the colligative property, they found the molecular mass to be this much, and then they might ask you to find the I value. So direct formula substitution, that's what they do, right?
Okay.
But 99% of times, right, the questions will be connecting I and alpha. That's why we spent so much time here. Okay. So they will give questions based on I and alpha, and then something you have to calculate. Say all the other colligative properties, 4 colligative properties can be calculated. That kind of questions only will come. Right. Any other questions? Yeah.
In I equal to calculated molar mass by expected molar mass. Calculated is the one using the when we add up all the.
No. Expected is what we expect. We already know how to calculate. Calculated is from the calculation of colligative property.
Okay, sir. So the abnormal one.
Exactly, abnormal. Correct. Okay, okay. When you tell it like this, I is equal to abnormal mass divided by normal is what we expect. Normal molar mass. Yes, that in this kind of way only they would have given in your textbook.
Sir, in the textbook it is the opposite way. Normal by abnormal.
Normal by abnormal.
Yes, sir.
No, that's what we don't have to confuse ourselves, right? You just go by the formula which I gave you. It's very simple. What you calculate from the colligative property divided by what you know for the formula. That's it.
Okay, sir.
Okay, fine. Anything else? Any other question? Okay, fine. I suppose there are no questions. Thank you so much, people. We'll meet again next week.
Thank you, sir.
Thank you, sir.
Thank you.